Okay, so this course covers Math 115, 116, and 216. We start with 215. So we do integration first, then we'll get into differentiation. And there's a reason for that, is that differentiation is highly technical and integration is not. We can learn about limits in a very easy setting by doing integration. And one thing you'll have to learn about me is that I look at integration as being at least two separate subjects, if not three. One is the notion of an integral is area under a curve, and that's the first thing we will do. And the other one is, if you've had a little bit of calculus and you've heard the word antiderivative, that's another notion of integration. It's the one that most engineers almost never use as a practicing engineer, and it's the one you're tortured about the most in Math 215, okay? That's just how it works. Math 116. So we'll break those up into separate concepts and deal with them as we go. So the big thing about this course is it does roll in applications. You'll get to see how calculus is really used, and it's fun. Calculus is fun when you're not lost in the myriad of algebraic and trigonometric details that makes classical calculus painful. Calculus is easy. The calculations associated with calculus is super tedious. It's not hard, it's algebra, it's trigonometry, it's stuff you guys are super good at or you wouldn't be at the University of Michigan. So anyway, we bring calculus alive through applications, but you know, there's lots of cool formulas that come out of calculus, and I'm not just going to say, hey, here's a cool formula without telling you how it actually comes about. So I will explain. There'll be derivations. You will not be required to regurgitate those derivations. My hope is when I go through that stuff, it's helping you to understand, oh, if I have a slightly different situation, I can make a different assumption and then understand how to get the formula. So you'll see how that goes. Chapter 1 is pre-calculus. We're going to do a little bit from it today for the first 40 minutes or so. And then we'll switch immediately into Chapter 2, which is setting us up to do Riemann integration in Chapter 3. All the grading and everything is explained on Canvas. I assume everybody's had access to it by now and downloaded the book, etc. On the Canvas page, right below the image of the book, is a link to a video that explains how to find things in the book. It's 600 pages. And if you look at that video, you'll see that it's actually quite easy to find stuff because all of the book is full of hyperlinks. You can jump from one thing to another. And Maisie has been indexed on the book. I broke it up into 5-page chunks. And so when you use Maisie, and it gives you links at the bottom, they're within plus minus 2.5 pages of where you want to be in the book. So you just open those up. So it makes it much more useful. Maisie, as the vanilla version, is not so helpful. There's really important notation. I'll define it as we use it, but you probably should read ahead in chapter 1.2 on just the mathematical notation. You know, notation is exciting. It's just like learning grammar, definitions. If many of you have learned other written languages, spoken languages, you know, the grammar's painful, conjugating verbs. So learning notation is similar to that, but that's just the way it is. The main thing I want you to get when you go through the notation is to understand that infinity is not a number. There's these things called integers, fractions, real numbers. But infinity is not a number. It's a concept. It's a limit when things get arbitrarily large to whatever extent, okay? It's not a number. Now, we'll talk about algebra using infinity eventually, but that's a little bit farther down the road. The students last semester did really well. I expect you guys to do the same, okay? So You can see the scores. The lowest score was a 72%, and I'm guessing the lowest score in the math courses is not 72%, okay? And these are not adjusted scores. Those are the actual raw, pure scores. So if you dig in, have fun, and take ownership of your learning, you can expect to have those good grades too. That's what I want to see happen. I want to see happy people. I want to see people coming and being engaged and asking me questions and pointing out my spelling errors. And when I say something and I write something else because my brain is not connected to my hand or something, call me out. And I'll get to know you, and you'll see that I don't bite, okay? Anybody believe that? I don't bite, okay? So we'll see. I write lectures out on a tablet. My handwriting is stupendously, notoriously, and Max, I'm going to have to ask you, I left my notebook up in my office, so if you'll go up and get the orange notebook and bring it back down. Oh, no, wait a minute. Here it is over here. Son of a gun. Whew, I'm not as brain dead as I said I was. We're going to start with a fundamental principle that was discovered in the year 200 BC. How about that? Okay. Oh, why don't they make room on this desk where I can have a notebook? Okay, so let's go a little bit higher. Yeah, okay. Can you guys still see most of the screens? Do you want me to turn on the side TVs as well, or with so few people, we're okay? For today, then we can do better. Okay, so let's get going. Come on. Pi and Archimedes approximation principle. So Archimedes, he's the person who said, give me a big enough lever and a fulcrum and I will move the earth, okay? That's the guy. So we know what pi is defined to be. It's the circumference over the diameter. Circumference over diameter of a circle. And we all know that pi is approximately 3.14159 ... And if I ask you for its value, you say, hey, that's no problem. It's a key on my calculator, okay? Or if I'm using Julia, I just do pi. Or if I'm being really fancy, I go \pi space, and I get the character to show up in Julia, okay? So pi is just something, we do it. But how was it computed in the first place? Right, it's a pretty abstract thing. You take the circumference of the circle divided by its diameter. You're going to go out and measure every circle circumference and every diameter and calculate ratios. So this is what Archimedes did in 200 BC. Before current era. So he had invented a means to compute pi to arbitrary accuracy. Can you believe that? 2,200 and whatever years ago, you could compute pi to arbitrary accuracy if you had the patience to do it. Means to compute pi whoops, I'm combining Julia and writing, okay? Pi to arbitrary accuracy. Okay, so let me introduce an image, because my drawing is even worse than my handwriting. And, oops, I want to go to the used ones. And Archimedes. Open. There we go. Okay, so just draw yourself a circle, and then sketch a hexagon inside the circle and a hexagon outside the circle. I'll give you a second to do that. Or just leave space in your notes and fill that in later as you wish, okay? All these images are in the textbook. So let n greater than or equal to 3 be a natural number. These are also known as counting numbers. So let me get myself a little bit of room. Now, depending on which math book you're reading, the counting numbers start with 1 or they start with 0. Can you believe we haven't even had a formal treaty, international or galaxy-wide, about where the counting numbers start? But they start at 1 in this course and most math courses, okay? 0 was invented a long time after people figured out how to count. In math notation, we'll write it like this, as kind of a bold N and a double line with N. So that's the natural numbers or counting numbers. And sometimes we'll write that set as 1, 2, 3, ... Okay, so there's the let n. And why do I want n greater than 3? Because here n equals 6. It's the number of sides I have on this hexagon. And if I had only 2 sides, I don't know how to do that. It'd be a line and then another line, and there'd be like no area, okay? So with 3, I can make a triangle, and I can put a triangle inside and a triangle just outside. Okay? And then on your hexagon, label the length of the outside part, capital L sub n, and then label the little one inside as little l sub n. And while you're doing that, I'll try to make mine a little bit neater. Okay, so how does that setup help us? Okay, so I'm going to define pi n upper is by definition equal to n times ln. So that'll give me the length of the sides. So for us, it's n equals 6. It'll give us the perimeter of the outside hexagon. I'm going to define pi n low, n times little n, and then we note that by construction, the way we've done this, pi is greater than or equal to pi n low and less than or equal to pi n upper. Okay, so pi is the perimeter of the circle, the circumference. And then n times capital Ln is n for the number of sides in our, what we'll call shortly, a regular n-gon, just a polygon with equal length sides, inside and outside. And Archimedes' idea was that if I take n larger and larger, I have a lower bound for pi, I have an upper bound for pi, and I can collapse them together and make the difference between the upper and lower bounds better and better and better. That's the idea. So how do you do that? Step one. The lower, also called inner approximation for the circumference, and because we've chosen the diameter to be 1, that circumference is pi, okay? We inscribe, which means to put it inside the circle. Whoops. I want the word regular in here, and I'll define that. A regular n-gon. So that means equal sides. So a rectangle would be a regular n-gon when it's a square, okay? That makes sense, the regular thing then, okay? Okay. And then step 2, for the upper, part of what we're doing today is you're learning the Rosetta Stone of Professor Grizzle's handwriting, okay? So something very simple. We're learning how to translate that into thought processes in your brain. How do you feel about that? Think you'll be able to handle it? Okay, so I've been teaching for a long time. All of my students have managed. I just haven't managed to get better, okay? So the next thing we do is we circumscribe a regular n-gon. And the circumscribe means outside. Okay. And then finally, the key step is we evaluate, compute the sides of these n-gons, and we have pi n just up is n times ln, and pi n low is n times little n. And then we define our estimate for pi. It still depends on n, the number of sides that we're using, as the upper estimate plus the lower estimate over 2, and this is a definition. And I've been using this symbol, and nobody's asked me what it means yet, maybe because you read the book. You often saw definitions done with a equal sign with a delta over it to mean definition, okay? But the problem with that is, do I mean the left side is defined to be the right side, or the right side is defined to be the left side? So what I do, and you don't have to do it in your homework solutions, the colon here means this symbol you haven't seen before, these symbols you know, and so I'm defining this new symbol in terms of things that have already been defined. So that's explained in the textbook as well. Okay, so it's just a good habit or bad habit or a habit that I've picked up. And then the error approximation is pi n up minus pi n low over 2. And so what we end up with is pi equals pi n estimate plus minus pi n error. So we have an expression which gives us a nice nominal value, and we'll compute some of these in a second. And what's really important, especially for engineers or for someone wanting to do math precisely, how good is this estimate? If it's off by 5, that's not a very good approximation of pi, okay? Now, if it's off by 10 to the minus 7, you're going, that's usable. Okay, so this is what we're going to be doing in calculus. So what's amazing is that 200 BCE, Archimedes, when he's not going to battle and killing, I don't know, Trojans, or maybe he was a Trojan. I don't remember, my Greek history is a little bit a long time ago. He wanted to compute pi. He was an amateur mathematician, and he came up with this idea of doing inner approximations with regular n-gons that he could compute, outer approximations, and he realized that as he took n larger and larger, he could make this approximation better and better. So what that looks like is this. Come on, do your thing, be nice. Okay, there's several n, it's not 6, I think it's 12, and that's probably 24 or 36 or something like that. You see how adding up the inside and the outside is getting closer and closer? Archimedes took it to an n-gon with 96 sides. Can you believe that? Come on. There we go, Archimedes table. Let's see how this guy did. Can you guys read that pretty well? Okay. So look, with our hexagon, the estimate was 3.2. It's not bad, okay? With doing a 24-gon, I don't know what that's called. 12 is a dodecagon. Anybody know what a double dodecagon is, okay? No, okay, so look, your error estimate is 0.013, and by the time you get up to 128, the error is 1 point something e to the minus 5, okay? So that's the essence of calculus. You have an object you want to understand, you want to compute it. We're going to be computing area here shortly. We know the area of a triangle, but what's the area of a heart? Or some other object like the link of a robot arm, okay? We come up with a lower bound for it, we come up with an upper bound for it as a function of a counting number, and we let that number get larger and larger, and then we try to prove that those two numbers collapse into the same thing, and then we're done. And that's what's happened here. Look, by the time you're at 128, the lower estimate and the upper estimate are the same to 4 decimal points. That's the notion of convergence that we will define precisely a little bit later, okay? The error estimate is the mean, the estimate is the mean of the lower and the upper bound, and then the error is the upper bound minus the lower bound over 2, okay? So this is what we want to retain. If we wish to estimate quantity x, we'll say, dot 1 form lower xn low and upper xn up approximations for x with, and here I'll put of course, okay? And you'll see what I mean. You want the lower approximation to literally be a lower bound for x. How close is it? We don't know. We have an upper bound for x. How close is it? We don't know. But if for large n, xn up and xn low approach one another, and I'm putting it in quotes because we haven't defined what the word approach means, but it will become the word limit by Monday, a common value, then we have a way to compute x with arbitrary accuracy. Way to compute x with arbitrary accuracy. And for the first part of the course, roughly the first 3 weeks or so, this simple principle is it. Now we have to get a little bit more precise on how we do the estimations, what the word approach means. So approach gives rise to the formal definition of limits. In chapter 2, but that's how we'll go about defining area under arbitrary curves. It's a pretty powerful method. Okay? And what do I mean by approach? Just like you have here, the table with pi low and the table with pi up. If we keep putting more and more digits here, the difference gets smaller and smaller, like we have here at 512, the error is down to 10 to the minus 7. And so you'd say, hey, I have computed pi. Archimedes went to 96 by hand. I want that on my desk by Monday morning at 8 a.m. No, but he didn't have a calculator. Come on. He had papyrus and I don't know what, a piece of charcoal? Okay. Give the guy his due. Okay. So you have any questions? You kind of get the idea of how you can take something that is abstract, a number like pi. Yeah, we just use it a key on our calculator, but how is the value really defined and how you do it formally? Make sense? Thumbs up, makes sense. Thumbs down, your really bad explanation. Okay, so great. Okay, so that's the main part of chapter 1. I'm going to put out something else just so we have a little bit of a group exercise. I see you guys are kind of grouped, except in the very back. Max, you may have to go back and form a group with somebody. I'm just going to give us a little problem. And the message will be, where is my, I don't want that, I don't want that. Come on. Okay. Here it is. So, my question, do we recall trigonometry? The reason I ask this is because calculus is easy. The hard part of this course is algebra and trigonometry. You guys think I'm kidding you, okay? But what drives students absolutely bonkers in their calculus courses is when they do the exams, they get a minus sign wrong and they get 0, okay? So here's the picture. Maybe I should make this a little bit smaller so we can get the questions on here too. So I'm going to give you 3 minutes, team up, and when I get it centered, it'll be go. So compute sine of theta as a function of x and a, so the right side is x. The lower side has absolute value because where this came from, a could be negative, and I didn't want a negative length on my triangle, okay, so it's positive. And it's a right triangle. The hypotenuse is the square root of a squared plus x squared, so it satisfies the Pythagorean theorem. You guys remember Pythagorean theorem? Yes, okay, so compute sine of theta, compute tangent of theta, and then, is this harder or not? Compute the sine of the arctangent of x over a. Team up. Just talk to each other about how to go about doing it. Introduce yourself. Hey, I'm Bill, I'm Jane, I'm whatever, okay? I'm Jesse, he's Max. And so those of you online, if you want to message each other in the chat, that's fine, okay? Or just work it, and you can type the answers in the chat as you get them for your online. That's perfectly correct thing to do. Okay, 1 minute is gone. It's the definition, right? He's asking me to remember something from high school. Oh my God. You're not being graded on it, so don't worry.
I haven't seen this in a long time.
You haven't seen this since you were like 15, 16? Yeah. How we doing? We got sine? Do we get tangent? What about the sine of the arctangent? Did you get that? You got it?
I think so.
Wow. Okay. Let's go through it. So what is the sine of theta? It is opposite over hypotenuse. Okay, so sine of theta equals x over square root of a squared plus x squared. Okay, Pythagorean theorem. What is tangent of theta? Shout it out. Opposite over, these are the things that I was taught in high school, except I went to a high school that did not even offer trigonometry. I had to learn it on my own. Can you believe that? Yeah, that's Jay, Oklahoma in the 70s, okay? So it's opposite over adjacent. So it's x over absolute value of a. Whoops. This is what I was saying. Oh my gosh. Please. Go back. Whew. But this is x over absolute value of a. Sometimes my hand is not connected to my brain. Probably never happens to you guys, right? You're young and perfect and everything. Okay, now, arctangent, what is that? It's the inverse of the tangent function, right? So what is sine of arctangent? If somebody's got it, shout it out.
X over
Oh, it's the sine of theta. Yeah, and why is that? Because tangent of theta equals x, I should have absolute value of a there, okay? That means theta equals arctangent of x over absolute value of a. And we already know that the sine of theta is equal to x over the square root of a squared plus x squared. So here the moral of the story is, if you didn't get it yourself, things that look hard often are not. So we're going to do proofs, not difficult ones, okay? This is not algebraic topology for freshmen, okay? This is calculus for the modern engineer. So we're going to do explanations of why things are true, and where young, inexperienced proof writers fall down is they forget that they have all of the information they need already given in the problem, because it's mostly applying definitions. Okay, so here what did we do? We applied the definition of sine, the definition of tangent, the definition of arctangent, and then it just fell apart. You see the message there? So we'll do that 20 times in this semester, okay? That's how you learn math. You just practice it over and over, etc. Okay, wow. You guys did better than I thought you would. I underestimated you. You gonna mark me down for that? No? Okay. Let's take a short break, and then we'll get started on a brand new topic. And if you have questions, type them out in Zoom. If you want to go get a pop or something to keep your eyes peeled open, because we meet for 2 hours. We're 8 minutes early on when our break should come, but I think it's at an appropriate point, so we'll just stop. So last semester I had a student from Ross who only had APA on calculus, so did not get the APB, so couldn't get the Math 115 credit. He did not have Rob 101, so did not know Julia. He had like JavaScript in high school. He struggled for 3 weeks and then ended up getting an A in the course, okay? So you're overqualified for this course, okay? Max, we have too few students to kick them all out. What do you think?
Yeah, you guys are good to go.
You're good I think you're good to go. You're going to do really well. Yeah. Okay. So here's something we're adding this semester. A little lecture check-in every once in a while. So if you're attending live, all you have to do is just pull this up on your phone and give your UMich email. And this works if you're online as well. So anybody who's synchronous, meaning you're on Zoom or you're in the classroom, you don't have to do anything. Now, if you can't come to lecture or you can't follow on Zoom, so you're asynchronous, then you will find this embedded in the notes that I will post, and they'll also be on this lecture recording. And then you need to write a 20 to 30 word summary of the lecture. Okay, so you guys have to do nothing except scan it, etc. Everybody got that down? Having trouble? You know, QR codes. Everybody loves QR codes. We got it? Okay, we're starting chapter 2. Yeah, so once again, chapter 1 is pre-calculus. It's assumed that you know it. The main thing I've done in chapter 1 is written it at a college level, advanced college level. So it's written in the same level of precision that you'll see in the other chapters in the book, which is usually quite different than what you saw it in high school. So when you read through it, I think you'll find it informative. So for example, if you had to compute x to power pi, what does that even mean? So x to the 3/2 means you take x cubed and then you take the square root, right? That's what x to the 3/2 means. What is x to the pi? Okay, so x raised to a real number. Well, whoops, where's pi is 3.14. You just keep approximating, okay? So replace pi with a decimal approximation and let that approximation get more and more accurate, and you take a limit. That's how you define x to a real number. And those kind of things you're reminded of them in chapter 1 if you scan through it. In high school, how many of you learned about Euler's number? In high school, wow. Okay, you've probably seen it in your Calc 1 and Calc 2 courses, of course. Okay, so do you know where Euler's number came from? Who invented Euler's number? Who discovered it? The trick question is Euler, right? No, Bernoulli, okay? And he was looking at interest rates, okay? He's looking at compound interest. You imagine having a checking account that paid 100% interest annually. Sign me up, right? I'm a university professor. We don't make anything, okay? Sign me up. And then he said, well, what if you compound that after 6 months, and then the next 6 months you get interest on your previous interest. And then you do it n times. And the formula you get is 1 plus 1 over n to power n. And then you let n get large and you get Euler's number. So stories like that are covered in the book. So I urge you to scan the book and go through and just pick up some mathematical culture. Make you feel good at parties. I mean, what's better at a cocktail party than being able to talk about where Euler's number came from, okay? Won't that make you popular? You don't believe it. You don't believe me, it's gonna make you popular. Yeah, it won't, okay? It won't, okay? So chapter 2. Max, if I start, and Kaylee, if I keep talking too much, tell me to focus on what we're doing here, okay? So calculus foundations. Proofs, finite sums, limits at infinity, and geometric sums. Yeah, that's a lot, but no, this part goes real well. So I'm going to post something that you don't need to copy down here, but just to set the tone for what we're doing here. Okay. So even though this is calculus taught by an engineer, we're going to build calculus from scratch, just like we computed pi, the number pi from scratch, okay? With a fundamental construction that anybody can do. And in your Julia homework 1, you'll even take that further, that whole idea, and apply it. And you'll compute the area of a circle using that idea, okay? In the textbook, everything is proven, essentially. Now, mostly the proofs are for other instructors than me who would follow on, and not all of them had the same level of math education I had. I went through all of the required courses to get a PhD in math. I was an engineer, but I just took the math prelim courses because I loved it. Multiple topology courses, differential geometry, etc., measure theory, function spaces. So all of the proofs are original, I wrote them, but they're written in a way that I think some of you are wanting to be a math minor, and you're interested in the proofs, okay? And you'll be able to read most of them because I've written them in a way that I think an undergraduate can get into them. But if you don't want to do the proofs, and what you really want to learn is how to apply calculus, that's in the book as well, because it's full of code. Now, the key thing about the code samples is if you go to the Canvas site and you hit pages, you'll have a link that gives you access to the Jupyter notebooks full of all of the examples worked in chapters 1 through 3, chapter 4, chapter 5, chapter 6. So you don't have to copy the PDF and paste it in and get a bunch of errors. You can open up and get the raw Julia code in the book. So the applications, you can reproduce them if you want. You're not going to be tested on proofs in any way, but our aim is to do enough of the reasoning behind calculus that it makes sense. That's the whole point, is that it makes sense. And hopefully the arguments will be almost as transparent as what Archimedes was, with a lower bound, an upper bound, and crush them together and get the value. They're not all like that, but a lot of them are. And so what is a mathematical proof? Well, I have a colleague who said, a mathematical proof is whatever it takes to convince a reasonable person that what you're saying is true. Now, he didn't define what a reasonable person was. That was the problem, okay? So it's supposed to be something that starts from a fundamental set of accepted hypotheses, and then you apply the accepted rules of logic. I like to think about it as this. There are many things that are intuitively obvious to the most casual observer, but they're false. And what a proof does is try to separate those two out, okay? So I'm going to help you be able to read math and tell when it's done right as a minor side thing, okay? The main thing is to teach you calculus and how to apply it. You ready to run? Out. I don't want any part of this. You're okay? Okay, that's good. So finite sums. Of powers of integers and proof by induction. And if you're wondering why, if you can add up 1 squared, 2 squared, 3 squared, 4 squared, up to n squared, the same thing with cubes, quartics, fifth power, kth power, you can calculate the area under any monomial. That's all it is. It's just summing up integers raised to powers. So means to determine area under monomials. And monomials are things x to power k, where k is 1, 2, 3, 4, 5, etc. Okay. So, once again, because my drawing is not so great, be nice. I selected you, I hit open. Okay, we'll try it again. Open, sesame. What's the magic word? Open. Okay. Guess what? Grizzle's going to draw. You guys ready for it? So that's an area under a triangle. Okay, so this is what we're going to go after. We're going to develop a method. We're going to apply it to a triangle because everybody knows the area under a triangle, right? Bottom, side, you multiply it, you divide by 2. Remember that one? Okay, but you don't know the formula for the area under, as I said, a heart or some other more elaborate shape. Those of you, you've all had Math 215, so you know the area under this, but maybe you've forgotten why it's true. So anyway, here's our objective. One plus 2 plus 3 plus n is n times n plus 1 over 2. So you want to prove that. And the method is proof by induction. What that consists of is the following. That P of n be a statement about the counting numbers. In other words, 1, 2, 3, 4, 5, 6, 7, about the counting numbers. With the following properties. It's called a base case. And the base case simply says P of 1 is true. Now, I realize at the moment, P of n, P of 1, that seems very abstract. We're going to make it very concrete in just a second, okay? We're setting up a framework, and then we're going to make it very concrete. So P of 1 is true. B is called the induction hypothesis. And it says, for all counting numbers k bigger than or equal to 1, if the statement P of k is true, then P of k plus 1 is also true. And the conclusion, when you have this, is that P of n is true for all n bigger than or equal to 1, the base case. I mean, you can kind of see how that works. If you have P of 1 and the induction hypothesis works, then you get P of 2. But if the induction hypothesis works, then you get P of 3. But if the induction hypothesis works, etc. Okay? So it's a it's a fact that induction is the same thing as the existence of the counting numbers, 1, 2, 3, 4, 5, 6, 7. The same properties that allow you to define counting numbers is the logical basis for the principle of induction. And that's how it works, so dot, 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 dot. Okay, so that's the abstract nonsense, okay? Let's apply this to our objective. Everybody, I can sense the tension because the word proof has been raised and we're doing one, okay, on the first day of class. What's it going to be like on the 13th day of class? Okay, we apply this to our objective, which is the sum of the first n integers has a nice closed form formula. Okay, so here is how we define P of n. We define P of n. I'm going to let L of n, by definition, be equal to the sum 1 plus 2 plus 3 plus dot, 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 n. If you had to guess what L stood for, and you said left, you'd be right. Okay? We'll define R of n as n times n plus 1 over 2. Yes. R is for right side of our objective. Okay. Let you write that down for a second. All right, fast but messy. I know I should slow down and get better, but it doesn't work that way. Okay, we just want to show that the sum of the first n integers is this, and then eventually we'll look at formulas for all the different powers and things, but okay. And then what we're trying to show is that L of n equals R of n. P of n is that L of n is equal to R of n. That's what we're trying to show. This is our objective. Show this. Okay, so I'm going to set it up where we can do this by induction. Okay, so we want to show that P of n is true, meaning that top sum is equal to n times n plus 1 over 2 for all n. Okay. Let's look at the base case. P of 1. And all P of 1 is asking is L of 1 equal, and I'll put a question mark over it because we don't know, we're going to check it, is L of 1 equal to R of 1. That's all P of 1 is. L of 1 is the sum of 1, okay? And R of 1, it's a little bit more complicated. It's 1 times 1 plus 1 over 2, but that equals 1. See that? So conclusion, L of 1 equals R of 1, and hence the base case holds. Now, sometimes the base case seems so trivial that it seems unsatisfactory to check it, but you always got to do it. But you can always go on and check the second one if you want. What is L of 2? It's 1 plus 2, which is 3. What is R of 2? It is 2 times 2 plus 1 over 2, which is 2 plus 1, which is 3. So P of 2 also holds, okay? So if you're nervous about, did I get something right on P of 1, just go ahead and check the next one. And if you really want to be more comfortable, check another one. But you don't have to. Induction says you start with the base case, okay? But you're free to check a few others. Now, this is the crucial part, the induction step. Does L of k equals R of k imply that L of k plus 1 equals R of k plus 1? If it's true, we're done. That's how proofs by induction work. And I've broken it down into little itty-bitty steps for us to check. Okay? And so what I always say is, let's find out. If for some of you it's totally obvious, I admire that. Okay, well, let's just check it out. So I'm going to compute R of k plus 1. So what is R of k? Well, R of k plus 1. Where we have n, we put k plus 1. So we're going to have k plus 1, and here it's going to be k plus 2. Okay, so this is equal to k plus 1 times k plus 1 plus 1 over 2, and that's k plus 1 times k plus 2 over 2. Okay, so checking that, just getting the formula for that, that's just algebra. Everybody's good with the algebra? Thumbs up, we're good, we can do that much algebra. Let's check out L of k plus 1. Any chance it's equal to R of k plus 1? Well, L of k plus 1 equals 1 plus 2 dot dot k plus k plus 1. What is this equal to? The sum of the first k, what is that?
Just the n times k plus 1 over 2.
Yeah.
Or k plus.
Yeah, so you're one step ahead of me, but that's L of k. And then you already just jumped ahead, which is fabulous, okay? I'm gonna break it down, so when you go back and look at your notes, that's just L of k. So L of k plus 1 is L of k plus k plus 1. So by the induction hypothesis, L of k equals R of k, which is k times k plus 1 over 2. That's the induction hypothesis. Okay, that's the induction hypothesis. Okay, so now we want to check, how does that work out? So now we know that L of k plus 1 equals L of k plus k plus 1. And that's equal to r of k plus k plus 1. Now we substitute in the k times k plus 1 over 2. So what are we doing now? Just algebra, okay? This is the thing that kicks everybody's hind end when they're doing stuff. It's just algebra now. Now we want to manipulate that and see if we get r of k plus 1. Well, we have a common factor here of k plus, whoops. We have a common factor here of k plus 1. So let me factor that out. So that's k plus 1. And then what's left over is k over 2 here and a 1 here. Right? And so now I'm just doing more algebra. Put this over a common denominator. Remember our high school stuff. And that's it. We're done. Because that's k plus 1 times k plus 2 over 2. And that was r of k plus 1. Okay, let you catch up on the algebra. Okay, so this is how typical proofs by induction work. And the hard part is setting up what is the statement about the counting numbers that I'm trying to show. And for us, it was looking at the sum of the first k integers, and we had a hypothesis for what that answer was, which was k times k plus 1 over 2, if we stopped at k, or stopped at n times n plus 1 over 2. And so what we're really saying is left-hand side equals right-hand side, so just write down what is the left-hand side and the right-hand side, and then turn the crank on the method of proof by induction. And so here's r k plus 1, k plus 1 times k plus 2 over 2. And here is L of k plus 1. And so we are done. Given holds for all n greater than or equal to 1 by the principle of induction. How many of you love proofs? Max, where are all the hands? No, I mean, not yours. Max just got through taking Rob 501, which is mathematics for robotics, which does 5 or 6 proofs every lecture. We won't do that many. We'll be lucky if we do that. Anybody online love proofs? No, we came to you, Professor Grizzle, to avoid proofs. Well, no, we're going to do enough of the logic so that you can understand where it's coming from, but you don't have to reproduce them yourself. There's only 1 or 2 homework problems total that have proofs. Okay. The textbook has formulas for 1 to the k plus 2 to the k dot, 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 plus n to the k for k bigger than or equal to 1. So we've just figured out what is the sum of the first n integers raised to power 1, and the textbook has it for powers 2, 3, 4, 5, 6, 7, all the way up to any number that you want, okay? So we will come back to that later, and we'll see why they're really useful. Okay, so at the end of the lecture, I'm going to paste in a chat, not a chat, yes, a U of M GPT prompt that will allow you to generate 4 examples of doing proof by induction with detailed explanations. Okay, so if you feel like this wasn't enough, there are more examples in the textbook, but I want to show you how to use the AI tools as instructors, how to generate examples that you can practice on. Okay, so Professor Grizzle only did 1 example. Yeah, but he's going to show you how to get 10 examples if you want them. Okay? Literally, it's going to be 4, but you can change 4 to whatever you want. Okay? Okay, so now we know the formula for the sum of the first n integers. The next thing we're going to study now is the heart of integral calculus, the amazing power of the rectangle. Finding the area under a curve. Okay, so for those of you who've already had Math 116, what we're going to be doing is things you know, but I think you're going to see it in a totally different light than the way you learned it in the math department. Okay, so another one of my beautiful, where did you go? Oh, there you are. Okay. Okay, so I don't know how detailed of a picture you want to make, or just say that go to the textbook and get this, but let's just discuss what this is, and then we're going to build on this picture. So here, we're just looking at f of x equals x. And so if we were doing the area underneath this, it's just the area under a triangle. And since this is f of x equals x, the slope is 1 in here, then the area here is just a half. But what am I showing here? I'm showing a lower approximation for the area and an upper approximation for the area. And the actual area of the triangle is bounded between these two, just like Archimedes for computing pi. Here's the same picture with n being a little bit bigger than 3. And we can see that we're getting better and better approximations for the area. Now, what I need you to imagine, or just go to the textbook and look at some more pictures, or I'll paste in some more in a minute even, is doing this when it's a much more interesting curve. So what you're going to do in your first project is I give you the data from an IMU on a drone collected in Professor Panagu's lab on the 3rd floor. So you have acceleration from the IMU, x, y, and z, and you're going to have to compute the position and velocity of that drone. Now, do you have a closed-form solution for what that acceleration is? The answer is no. You have data points coming out of a sensor. These are what engineers do. And you're going to now, so all this stuff you did in Math 116 where you integrated sine, cosine, and exponentials and stuff, just throw it away. You're not going to see that many things in terms of robot trajectories that have that, okay? You need to deal with much more general situations. And so what we're setting ourselves up is to be able to do that. You with me? Okay, so that's why we're doing that. So, very good. So let's apply Archimedes' principle. Whoops, come on. Let's apply this 2,200 years old principle to compute the area. Okay, so the good thing about the case we're working on is we know the answer. So we can check how the method works. You're going to see the lower bound and the upper bound. You're going to see how they depend upon n, and you're going to see why we need to understand limits, okay? So that's what's all going to happen here as we do it. Questions? Excited? Okay, Max, I need you to invent for me a truth meter. And I want to know when I say they're excited and they say yes, who's lying to me, okay? You'll work on that? That's a good engineer? Okay, so I'll draw it so that you can draw it. Come on. Extend. Thank you. Thank you. Okay. So I'm going to label this A equals 0, and some point out here, B. So we're going to get area from A to B. What a color. Make that nice bright red. So this is just y equals x. The slope doesn't look like 1 because it's not drawn to scale, okay? Give me a break, okay? And then we're just going to chunk this up. Okay? And this will be labeled xi, and this will be labeled xi plus 1, x sub I plus 1. Okay? And so our curve is f of x equals x. Okay, so now I've got to do some definitions. I'm going to let delta x be b minus a over n, where n is some number bigger than or equal to 1. So this is just b over n because a equals 0. And so here, n greater than or equal to 2 or something. Okay? Really, we want to let n be 200 million to power 47 or something, okay? Something big. Associated with this delta x, we have a nice regular grid. A equals x1 less than x2 less than x3 dot 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 less than xn less than xn plus 1, and that's equal to b. So 0 is A, the way I'm doing my triangle. And the xi's are defined by xi plus 1 equals xi plus delta x. Okay, so x1 is 0, x2 is delta x, x3 is 2 delta x, x4 is 3 delta x, etc. So xi, you can work this out, it's I minus 1 times delta x. And this just means multiply, okay? It's not the dot product that you did in Rob 101, but I find ugly in formulas, but to sometimes emphasize the product, I just put a little dot. You're good with that, you'll survive. Okay, so it's not a cross product, it's not a dot product, it's just multiply. It just means multiply. Okay, so we use the intervals xi plus 1 to define rectangles. Okay, and I'm going to do a little blow up here. And I'm going to deliberately not make the curve equal to a straight line so that you understand that what we're doing here is going to apply to more general things. But I'm going to make a rectangle from xi to xi plus 1. Okay? And this is going to be the lower approximation. And this height is going to be height. Whoops, I want that to be black. Come on, go away. This, come on. I know, you haven't been used since. Okay, so hi low is f of xi. Now the f we're going to be applying it to right away is going to be f of x equals x, etc., but we're setting it up more generally so I can plug in different f's later on, okay? So this is the thing we have here. And the beautiful thing about a rectangle is everyone in the room knows the area of that rectangle. Width times height, okay? We know the area. Okay? So there are n rectangles. Defined by the n plus 1 points x1, x2, dot, 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 xn plus 1. And xn plus 1 is b, and a is equal to x1, and we're taking that to be 0. And even I have a hard time reading that, so I'll fix that. Okay, so we have one more point than rectangle because it takes 2 points to define a rectangle. So you have one rectangle, it takes 2 points, okay? So you need one more point than the number of rectangles. That's the lower thing, okay? So AI low, simply by definition, HI low, the height of the rectangle, times delta x. And as we said, that's f of xi times delta x. Because we're doing a simple triangle with slope 1, f of x is x, so f of xi is just xi times delta x. And we'll remind ourselves that xi is I minus 1 times delta x, and then just write that in. So that's where it comes from. Okay, so that's the area of the ith rectangle under this curve here. So the ith rectangle. The first one, it's 0 because the height is 0 on the left. So here n is 4, and then it's 0.25, 0.5, 0.75, and then we don't get anything, we use it all up. Okay, so that's all we're doing. And we see we get a lot better approximation, we let n be large. So that's the area. And so the whole area, so this is calculus. We're going to define area n low, the lower approximation is by definition equal to A1 low plus A2 low plus dot, 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 AN low. Now comes a bunch of algebra. The calculus is done, okay? We've defined a lower approximation for the area. Now we've got to just compute it all, okay? So that's the sum, I equals 1 to n of AI low. That's the sum, I equals 1 to n of our formula we had. Oh, I made a mistake here. xi has a delta x, here's a delta x, so this is delta x squared. My apologies, going too quick here. So we need the AI, and there's a delta x squared here. Now delta x is constant, it doesn't vary with I, it's fixed with n, it's b over n. So I'm just going to put the delta, in fact, let's make it a little bit, come on, yeah, delta x squared, and then it's multiplied by 0 plus 1 plus 2 plus n. Does that look familiar to us? Okay, I just took the sum, I equals 1 to n. I plug in I equals 1, I get 0. I plug in I equals 2, I get 1, dot, dot, dot. I plug in, and this should be n minus 1. I'm glad I turned my brain on here. So that's n minus 1. Okay, so then we've got delta x squared times the sum, I equals 1 to n minus 1 of I. So delta x, that was b over n. We've got that squared. And we know the sum of the first n integers, and now n is n minus 1. So I'll just plug in n minus 1 into our formula. Okay, so the only shortcut I took is the n minus 1 plus 1 I just wrote as n. Okay, so that's really n minus 1 plus 1 from our induction formula. And you're waiting with bated breath, I can tell. So that's b squared over n squared, our algebra. And then this is n squared minus n over 2. Painful algebra. This is why calculus is hard. It's not because the calculus is hard, it's because the algebra is hard. Okay, and then what I'm going to do is move the 2 here. So let me put that in red so it's clear what I'm doing. There's a 2 go away here. Well, I wanted those to be blue. I wanted that to be red. Give you a chance to catch up. Okay, so I just swapped the positions there. Okay, so then we do a little bit more algebra, and we get b squared over 2 times 1 minus 1 over n. Whew. So that's our lower bound for the area under a triangle. So let's just plot it. Okay, so let me just emphasize that all of this grunge, that's just algebra. Okay, we've got this nice formula, b squared over 2, b squared over 2. What's the area of this triangle? The base is b, y equals x, so the height is b, so the area is b squared over 2. That part we recognize, and then it's times 1 minus 1 over n. It's a lower bound, because we took triangles that were always lower, rectangles that were always lower than the maximum height of the triangle under between xi and xi plus 1. Okay. And I'm just going to plot 1 minus 1 over n. This is n. Come on, this is 1.0. And so n is 1. I get 0. When n is 2, I get a half. When n is 3, I get 2/3. Whoops, 2/3, when 3/4, etc. Okay, so we can see that the 1 minus 1 over n approaches 1 as n becomes large. Okay, so that's our lower approximation for the area of the triangle. So the lower approximation looks like this. Then we're going to now do an upper approximation, but we won't do all of the algebra because you've already gone through it once, okay? So, but you see how it works? When you have a function f of x equals x, we end up summing integers to power 1. And that's where the sum of integers came in, okay? Okay, now for the upper approximation, and we'll be quicker here. Because if I grind this out, you guys are all leaving, I know it. Left out a the, but I'll put it in for the upper approximation. Okay, so we do the same thing. I draw my curves deliberately so that it's not f of x equals x, and I blow this up so we can see what's going on. Okay. And so this is an upper approximation of the area under this curve. Okay, so we have f of x here, and hi up is f of x I plus 1, because when the curve is monotonic, the highest value is on the right-hand side. And as when we're doing the lower approximation, the lowest value of the curve is on the left-hand side. So instead of where hi low was f of xi, that's the only thing that changed. Okay? Then we do the same thing, except we don't write it all out. Hi up hi up times delta x, and we would call that delta x is b over n. So this is f of xi plus 1 times delta x, and xi plus 1 is equal to I times delta x. Because we are doing a line, f of x equals x, this is just xi plus 1 times delta x. And then this is I delta x. Once again, algebra. I delta x squared. Whew. Okay, so that's our formula for the upper approximation of an individual rectangle. And then the area.
We got a question.
Oh, sorry.
Yeah, sorry, my question was, so with the I plus 1, doesn't the plus 1 mean that n automatically has to be 1? So then like how can you have a plus 1 and a variable n? Does that question make sense? Because n is the...
Here, the xi plus 1? Is that what?
Isn't n the number of separations? So wouldn't that change like the width of the rectangle? But the width of the rectangle would just be 1.
Yeah, so, okay, let's go back. So here we have n rectangles where you can't really tell. I guess you got 1, 2, 3, 4, 5. We can count them, okay? So n is, say, 100.
Oh, wait, I think I realized what I was saying. I think, so I was assuming that xi plus 1 is just like one unit to the left, but it's just the next.
So it's this is an array.
Yeah, okay.
Yeah, so, and it's my bad handwriting makes it sometimes look like it's xi plus 1, but it's x sub I plus 1. My apologies, okay? So this is where today's lecture, learning how to read the Rosetta Stone of Grizzle's handwriting is really important, right? Yeah, sorry about that. So the index, I is an index, and this is an array indexed by I. Okay, so all we're doing is just getting a formula for the area here. And if that function was e to power x times sine of x cubed, you just plug that in, okay? Now, doing it analytically would be really painful. But what did we do here? We just, it's okay. Oh, this is 6:20, so we are going to stop here. What I'll do is just simply paste in the prompt, and you guys will be able to download the rest of the notes.